Hi, and welcome to this lecture where we will discuss clandestine communications and ciphers. We're going to start out by talking about why people use secret communications and also discuss the different opportunities that arise in terms of intercepting this kind of communications, localizing them and breaking the codes used, but also the kind of vulnerabilities you have to watch out for to make sure that you are not the one getting your communications intercepted or your transmitters localized or your ciphers broken. We're also going to look at a Cold War case study which shows how some of these technologies were actually used. And finally, we're going to take a look at ciphers in more detail. How to use ciphers using nothing but pen and paper, as well as how to break ciphers using nothing but pen and paper. And finally, we're going to see how well does modern AI perform in breaking some simple kinds of ciphers. And I think that the results may surprise you. I know they did actually surprise me.
The goals for this lecture are, first of all, to learn some more about clandestine communication. We're going to talk about how clandestine communications are used to exercise command, but also what they mean in terms of secrecy. We're going to discuss wavelengths and frequencies and how these two terms fit together, as well as number stations, what they are and if they still exist. We're going to talk about ciphers, specifically what a monoalphabetic cipher is, and a one-time pad, how that works. We're also going to take a brief glimpse at code breaking, specifically how to use frequency analysis to break, for example, a monoalphabetic cipher. So during this lecture and afterwards, I would encourage you to reflect on how classic cipher techniques like the one-time pad could potentially be combined with modern technology. So, clandestine communications. One of the reasons to use clandestine communications is because it allows you to secretly control agents, for example, in both peace and wartime. So if you are an intelligence organization, you need some way to exercise command. And in order to exercise command, you have to communicate with people. But since these are secret assets, either intelligence officers or recruited agents, you need to be able to communicate in secret with them. But it can also act as a constraining factor because there is always a risk of micromanagement. If you have too much in terms of communications, then maybe you will be tempted to try to micromanage people to the slightest detail. And this is typically not an effective way of doing things. It also forces various units, either military units or intelligence officers or agents, to some extent stay in contact with their superior officers. So this can also be a potential risk, both in terms of what happens if this contact is interrupted, but also in terms of that it can be a potential vulnerability. The second dimension here is secrecy, because this presents an opportunity. If you can localize the enemy's agents and intercept their traffic and break their codes, this presents an opportunity for you, because this will give you insight into what the enemy is doing and also potentially give you an opportunity to trick them. But the same thing also means that there is a vulnerability. You too may find your communications intercepted, localized, and your codes broken. So you need to be able to both exploit this vulnerability in your opponent, but also protect your own communications at the same time to prevent your enemy from doing the same thing to you. So what this means is that there is a secrecy dimension and a command dimension. And both of these have both negative and positive aspects. So in terms of secrecy, the negative aspect is of course that it presents a vulnerability if you use this kind of clandestine communications. But the positive aspect is that it gives you an opportunity when your opponent does. In terms of command, of course, there's always a risk that you are constraining your secret assets by staying in touch with them. But on the positive side, it allows you to command them, to exercise control, and to use them to their full potential.
Now we're going to talk about radios, because radios are very important to understanding these Cold War case studies, and radios are still used today, so learning about how radios work is as useful as it ever was. We're going to talk about wavelengths and frequencies and how these two terms fit together. We're also going to talk about direction finding, how it works in practical terms. And we're also going to look at the mysterious numbers stations, which were a Cold War phenomena. And actually, a lot of these number stations are still operational. And just to give you an example, I'm going to play you one of my own intercepts that I've done using my own equipment.
The first thing we need to learn about is wavelength and how wavelength is tied together with frequency. So as you can see here, we can measure wavelength in meters because it's a measure of distance, and we can measure frequency in hertz. As you can see here in the figure, the radio wave has these peaks. So from one peak to the next peak, that is 1 hertz. So for FM radio, which is what you would be listening to in your car, you have 88 to 108 megahertz. That means that you have between 88 and 108 million of these waves every second in the signal. And between each of these wave peaks, there will be a distance of about 3 meters in this invisible wave. For shortwave, which is a lower frequency, that spans between 3 megahertz and 30 megahertz. And what that means is that on the 3 megahertz range, the wavelength will be 100 meters. And for the 30 megahertz range, it'll be 10 meters between these peaks in the wave. But if we go all the way down to medium wave, which is even lower frequency, this goes between 300 kilohertz, which is 300,000 hertz, all the way up to 3 megahertz, which is 3 million hertz. So at 300 kilohertz, the wavelength is almost 1,000 meters, whereas 3 megahertz means that the wave is 100 meters long. And the reason this is useful to know is because the frequency and the wavelength has a direct relation to the kind of antenna you need to use to be able to receive these different signals. So if we look at a table of wavelengths, we can see that at the top here we have the very low frequency, between 3 and 30 kilohertz, where you have these huge wavelengths, 100 kilometers to 10 kilometers. And then we move through the spectrum to low frequency, medium frequency, and then we have high frequency, which is interesting because high frequency allows for very long range in terms of radio, and that is why it's still used to this day. Then we have VHF, which is very high frequency, 30 to 300 megahertz. This is where you find most commercial walkie-talkies that people use in law enforcement and security, for example. And then you have UHF and SHF, which is ultra high frequency and super high frequency. This is where you find Wi-Fi, for example. And then you move up to even higher frequencies. I could also add that the lowest frequencies here are actually also used to some extent still to this day, because the very low frequencies can penetrate water, which is something the other frequencies cannot do. So you can actually communicate with a submerged submarine with the very low frequencies, and that's why they are still used to this day. Now let's talk about direction finding. Let's assume that you have your clandestine transmitter at the Department of Political Science in the building called Eden here in downtown Lund. Now let's suppose that your opponent has a listening post out in the Nova area at the mall. And they are able to not exactly pinpoint your signal, but they can detect which direction your signal is coming from, as you can see here. So there's a margin of error, and they don't know the distance. They can only determine the direction of your transmission. But if you have a second listening post at the hotel up at Eden, then they can also determine the direction your signal is coming from. Again, they can't tell how far away it is, but they can tell with an approximate direction. And then you add a third, typically, and this one will be to the south at another hotel. As you can see, there is a specific place now where all of these different lines intersect. That is where we will find the transmitter. So this allows us to identify a fairly small area that we can search in order to find this transmitter. And that's how direction finding works in principle. A very interesting and very useful characteristic of high-frequency radio, also known as shortwave, is that in these frequencies, the radio signal can potentially bounce off one of the atmospheric layers that exist in the ionosphere. So as you can see here, during some parts of the day, the signal will most likely go through this layer and out into space. But an interesting thing happens at night. And at night, the F1 and F2 layers merge into just F layer, and the D layer disappears. And what this means is that this combined layer makes it possible for radio transmissions to bounce down to Earth again. So as you can see here, you can get a first bounce, and then it bounces off the Earth, goes up and bounces in the atmosphere, and then it goes back down to Earth. And this means that there are so-called skip zones where it will be difficult to detect these transmissions. But if you can calculate this and try it out, then you may be able to identify good bounce positions. And this will give you vastly improved range for your radio, even with fairly weak transmitters actually. This also depends on solar conditions, because the ionosphere is ionized by the sun. So as you can see here, we can pull up solar terrestrial data, and this gives us, it's kind of a weather forecast for different propagation conditions. So if you look at the column to the right, you can see HF conditions. So if you have a wavelength of between 80 meters and 40 meters, you can see that for this particular date, May 21st, 2025, the conditions during the day were poor, and during the night they were fair. But for 30 meters to 20 meters wavelength, you had good conditions both during the day and the night. Then fair for the high frequency, and then poor. So if you have this information, you would know that, okay, so for this particular day, I should use the 30 meter to 20 meter wavelength, and that would give me good range for my radio transmissions. And this brings us to the concept of numbers stations. So number stations, as you can see in this picture, they use shortwave, and this means that they have to have pretty significantly large antennas, because shortwave means that their wavelength is longer, and that means your antenna also has to be longer. But these are very, very powerful transmitters. And because of it, you can actually tune in these number stations with even a fairly common, fairly affordable kind of what's known as a world radio receiver. A receiver that is capable of receiving shortwave transmissions, like the one in this picture, which is actually my radio. You can use the built-in antenna, which is probably going to be a little bit difficult unless you have very good conditions and you're standing outdoors, or you can actually connect it to a wire antenna, which is quite a bit longer and works quite a bit better. So a number station is simply a station that broadcasts numbers, typically. In most cases, this means that there's a robotic voice just reading out different series of numbers. These numbers are coded transmissions. This means that these communications have been encrypted in some way. And typically this is to keep the contents of this message secret. So the recipient will have an encryption key and be able to decipher it. But these transmissions typically use a very secure kind of encryption called a one-time pad, which is theoretically impossible to break, even with modern computers. So this is actually a very secure way of communicating, but it's also a one-way way of communicating. So these powerful transmitters send out a message to specific recipients, but the recipients are not able to answer these transmissions, not using radio. They have to have another way to send the reply, as it were. If you use software to receive radio, it can look something like this. And this is the software I run on my computer, and this is hooked up to my antenna, which I have at home, which is 32 meters long. And just to give you a bit of a sample, this is how the Russian number station M12 sounds like. Now, you might wonder, why did this number station use Morse code? It's, after all, not 1920 anymore, so why is this so interesting? Well, as you can see from these examples I've shown here, Morse is also known as continuous wave in radio circles. And if you compare a continuous wave signal with a voice signal, even a compressed voice signal, which is known as single sideband here, you can see that the Morse signal uses a very narrow bandwidth. It's very, very efficient. And this means that it's easy to filter, because you can filter out everything except that very narrow peak. Whereas if you have voice, you have to capture a lot more bandwidth in order to make sense of it. So Morse is actually still to this day, very, very effective. Another thing that makes Morse very effective is that you can receive it without having any kind of sophisticated digital or computerized equipment to decode it, because the decoding happens inside the brain if you are trained in Morse. And the brain is actually surprisingly effective kind of modem in this case, because the brain allows you to correct for minor errors or poor reception or static, and it actually is quite effective once you've learned how to use it. If we look at the Asen Giorgiev case, the first thing we need to look at is this handwritten note that was found by the Bulgarian security service in the home of Asen Giorgiev. So what do these numbers and words mean? Well, by now we know enough to actually decipher this, because the first part is the frequency. And 5243 kc means kilocycles, and kilocycles is an older term that means kilohertz. So it says 5243 kilohertz. And it also says 57 meters and 5.243 MC. And MC is short for megacycles, which is an older term for megahertz. And as we've learned by now, 5.243 megahertz is the same thing as 5,243 kilohertz. It's just two different units. And as for 57 meters, well, if we look at the frequency table we discussed before, we can see that 5.243 megahertz places it in the high frequency range, i.e. the shortwave range, because 5.2 megahertz is between 3 and 30 megahertz. Now, if we perform a wavelength calculation based on this, 299.79 divided by 5.243 megahertz, that gives us 57.7 meters as the wavelength. And that explains why he's written down 57 meters. So all of these three rows at the top mean the same thing. They are basically a frequency and a wavelength. So the second part is the transmission schedule. It says 9:30 o'clock, 5 minutes of music, first and third Friday of the month. Friday, i.e. it says Friday 1 plus 3, which means first and third Friday of the month. And then starting message 11. And this is Asen Giorgiev's one-time pad. And to understand how a one-time pad is used, we need to move on to the next segment, which is ciphers.
Now it's time to look at ciphers. As you have learned by now, ciphers are very important to keep your communications secure. We're going to look at first a very simple kind of cipher using nothing but pen and paper, and then a very secure kind of cipher that also uses nothing but pen and paper. We're also going to discuss how you can break simple ciphers using nothing but pen and paper and a frequency table. And we're also going to test out how does a modern AI perform in breaking one of these ciphers. And I think the results may surprise you.
The first thing we need to learn is the definition. So the definition of encryption is to make a message unreadable to anyone but the recipient. So you don't have to actually hide the message. You can make the message available, but it's still unreadable because it's encrypted. This is the idea behind number stations. Anyone can tune in a number station, but you won't be able to make sense of the message because the message is protected by encryption. So what is the purpose of encryption? Well, to protect information in transit. So it doesn't have to be written. It can also be spoken. You can use, for example, voice garbling encryption devices, and you can also speak in codes and so on. The methods to achieve this can either be manual, using pen and paper, or they can be technical and automatic, using different kinds of devices, electronic or mechanical. It's important to keep in mind that for encryption, there's always a time factor. And that means for how long does the information need to be secure? So in a tactical setting, you have different requirements compared to a strategic setting. For tactical setting, maybe it's enough if the information is secure for a few minutes or a few hours. So if you're going to tell someone in your squad that we need to assault this bunker and we need to coordinate ourselves and do it in 2 minutes from now, then in 10 minutes from now, that doesn't matter anymore. It only has to be secure for the next 2 or 3 or whatever minutes. Some cases, maybe you need to keep your information protected for a few hours, but that's it. So your code only has to be secure enough to make it impossible for your opponent to break it within this short time span. For a strategic context, on the other hand, maybe you need to keep your information secure for several years or even decades. And that, of course, means that you need a much more secure kind of encryption, something your enemy can't break even if they put a lot of time and effort into it. One of the most simple kinds of cipher is the so-called monoalphabetic cipher. This means mono means that it's just one and it's alphabetic. So in this case, you take the alphabet and then you just move the letters around more or less randomly. So as you can see here in the table, I just rearranged all the letters into a new alphabet, if you will. So that is simply a monoalphabetic cipher. It's very weak, but it's also very simple to use. If we use our new monoalphabetic cipher I just made to encrypt the text, we have been discovered, move out at dawn, go to meeting point Adam at Portsmouth. And then we just write down the letters of our message like I've done here. And then you just look at the table I have put below. And then you can see, okay, so the letter W, that means that we write M instead. For the letter E, we write I. For the letter H, we write T, and so on. So you just shift the letters around using this encryption key that I have put down here below. However, there is a key vulnerability here, and that is that, for example, these so-called bigrams, which is when you have two letters next to each other, these are very common words. We, at, go, to, and as you can see here, the at bigram will always be encrypted as BZ using this monoalphabetic cipher. So a code breaker would be looking at this kind of thing. Repeating patterns like this are key for breaking this kind of cipher. And here is the encrypted message without any spaces, because you would typically want to remove all the spaces to make it more difficult to break the code. However, you can still carry out what's known as frequency analysis. And here I've run a frequency analysis on this encrypted text, and it shows that the letter I is the most common one in the crypto text, followed by V, Z, B, G, and so on. And it also gives me the exact frequency of each letter in terms of percentages. Now, if I know that this message is written, that the clear text is in English, I can look at a frequency table for the English alphabet. And in the English alphabet, E is the most commonly used letter. Its typical occurrence is 12.7%. So that means that the letter I in the crypto text is probably the letter E in the clear text, because they are the two most common letters in the crypto text and in the real alphabet, respectively. So what I would do here is, first of all, I would replace the letter I in the crypto text with the letter E, and then we can test and see if that is actually correct. Of course, just one letter isn't enough to be able to tell if it's correct or not. But here's an interesting thing to look for. There are two E's in a row here, and I know that that is a pattern that does exist in the English language. So that would point towards this being possibly correct. Now I can move on with two other letters. So if we have two E's, then there is a limit to the kind of letters that can go before and after. So let's look at, first of all, letter P, which has a frequency of 1.54%. And then after that, we have the letter G, which has a frequency of 6.15%. So these two are quite different from each other. So what could this correspond to in terms of the real alphabet? Well, the letter B has an occurrence of 1.5%, and the letter N, respectively, has 6.7%. So as you can see, these are quite close to the frequencies in the crypto text of G and P. So based on this, I will guess that I can put B and N into the text as well and cross them off the list. Because remember, each letter in the crypto text corresponds to one specific letter in the clear text alphabet. So once I've eliminated one letter, I can move on to the next letter. Now let's look at the letter B in the crypto text. It has a frequency of 9.23%. And sometimes in a short message like this, you cannot expect to have exact correspondence between the frequency in the crypto text and the frequency in a longer text, which is what the real alphabet would show. So in this case, we'll try to see if B might actually be A, because they are quite similar in frequency. And then we'll input that. Then we move on to Z, and C has as you can see here, a frequency of 12.31%, which means that we should put it quite high. So let's go for the second highest in the clear text alphabet. And then we move down the list with O, which is the fourth most common letter here in the real alphabet, but it's the second most common in the crypto text. So then we keep crossing them off like this, and now for X, and then we move on to the next letter and the next letter, and so on. And as you can see, gradually this clear text message is starting to emerge, and you probably will not have to break all of the letters in order to be able to make out what it says. So, for example, just by looking at it, especially if you have some experience with crossword puzzles and such, you can probably make an educated guess here at what letter corresponds to what letter in the alphabet. And then you can just try it out and see if it works. And by doing so, you can break a message like this. I'd say somewhere between 20 minutes and maybe an hour should be enough to break a message of this length, depending on how lucky you are with the frequency and how much it corresponds to the real frequencies. But typically there won't be that much of a deviation in a normal kind of sentence structure. So what happens if you try to break this code with ChatGPT? Specifically, I tried it with GPT-5. And if I tell ChatGPT, this is a monoalphabetic cipher, the clear text language is English. And then I tell ChatGPT, I asked actually first ChatGPT, can you break this cipher? And ChatGPT said, yes, I can. So I said, okay, fine, go ahead and break it. And then ChatGPT was churning this for 9 minutes and 19 seconds, as you can see. And then it says, thanks, I got it. And then it actually said that the clear text message is, nothing in life is to be feared, it is only to be understood, and attributed this to Marie Curie. And as you know by now, that is the wrong answer. It does not actually say that. It says, we have been discovered, move out at dawn, and so on. Not only is this explanation wrong, it's logically impossible, because we know it's a monoalphabetic cipher. So we know that there is a pattern to how these letters repeat. We know, for example, that the part where it says D-I-P-I-I, that there has to be, the letter I has to first occur as number 2 in this string of text, and then it has to be repeated several times. And that doesn't match the translation offered by ChatGPT. So ChatGPT is not only wrong, it gives you an explanation that is logically impossible. A human with a rudimentary knowledge of this kind of code breaking would not make this kind of mistake, because they would know that it goes against the rules of how a cipher like this works, simply. But there are other kinds of software you can use. There's, for example, a Python script you can download called Subbreaker, which works a lot better. So here I tried using Subbreaker on my own laptop. I gave it the command break. I specified language English, and then I simply pasted the text string, which is the same text string I gave to ChatGPT. And the first guess was wrong, but it's logically possible. And here it offers a fitness score, which is something that allows you to see how good a guess this script arrived at. So fitness score 97.59 means that this is how many potential real words this string matches. And as you can also see here, in this very short time, 4.4 seconds, this script tried 824,525 different keys. It was able to try 187,010 keys per second. But it was still wrong, and I can see that it's wrong because it doesn't look quite right. U for bean, city, R, you see, it doesn't make any sense. So I ran it a second time. This time it took 8.2 seconds to complete, arrived at a higher fitness score of 97.85. So you can see that the score is higher than it was in the first run. It tried also a larger number of keys, and now it arrived at the correct explanation, which is, this is the actual message that was encrypted. So it broke the cipher and gave me the correct plain text. We have been discovered, move out at dawn, go to meeting point Adam at Portsmouth. There is, however, another kind of encryption also using pen and paper that is much more secure. And this is the one-time pad, or usually known as the OTP. So as you can see here in the illustration, a one-time pad is typically comprised of a number of letters or numbers in a series like this. In this case, you have all the letters in blocks of 5, which is a fairly common way of doing it. The interesting thing about a one-time pad is that it is theoretically unbreakable at this point in time. So no computer that exists and is operational today is capable of breaking a perfectly generated and used one-time pad. However, in order to be theoretically unbreakable, there are 4 conditions that have to be fulfilled. The key used to encrypt the message has to be randomly generated. This may sound trivial, but it is actually quite difficult. Most computers are not able to generate perfect randomness. Instead, a computer will typically generate something known as a pseudo-random key, or a pseudo-random sequence. So this limits the security of the one-time pad to some extent, but if it has a high level of randomness, which a computer should be able to generate, then you will still have a very secure type of encryption. The other condition here is that the key has to have the same length as the message. So you have to have a very long key, and you can only use a key once, then you have to destroy it. So you can never reuse a key. If you do, you will immediately compromise the strength and security of this encryption scheme. And of course, you have to keep the encryption key secret to everybody except the other person using the encryption. So if you are the one sending, then you use your copy of the encryption key to encrypt your message. Then you destroy the key you have. The recipient will take their copy of the key and use it to decipher the message, and then they will destroy their copy of the key. And after that, if anyone should happen to find the encrypted message somewhere, then it will be impossible to break it, because now both keys have been destroyed. If we use this table of letters and numbers we used before, where we have simply numbered all of the letters of the alphabet, and then we take this example message, test message for UNDD01. Now, if we plot so that all the letters have their corresponding numbers below them, as I've done here, then we simply add the key. Here is our randomly generated key, which we will only use once. And for the key, we also translate each of the letters into the corresponding number using the table and write it below. Then all we have to do is add these two numbers. The numbers we have derived from the test message, and the numbers we have derived from the key. As you can see, this is a matter of very simple addition. So you can do this in your head without too much effort. And then the perhaps somewhat tricky part, until you get used to it, is that after this you have to apply something called modulo 26. What that means is that for every number that is higher than 26, you have to subtract 26. So this is just to ensure that you will get a resulting number that corresponds to a letter in the alphabet. And since there are only 26 letters in this alphabet, then we use modulo 26. And if you use a Swedish alphabet, for example, you can just change the modulo number so that it corresponds to whatever alphabet you're using. So, for example, you could have modulo 29 instead, and then you just simply subtract 29 for every number that is higher than 29. But in this case, it's modulo 26, which is the typical for English language alphabets. So as you can see here, the first number is 40. The first of the added numbers is 40. So if you subtract 26 from 40, you get 14. And the second number is 30, which is also higher than 26. So if you subtract 26 from that, you get 4. And same thing with 32 and 37, which becomes 6 and 11 respectively. But for the letter E and M, the M letter in the test message and the E letter for the key, you can see that the sum is 18. And 18 is not higher than 26, so then we simply move 18 to the row at the bottom. And then we have the next sequence where we also subtract 26 from all the numbers that are higher than 26, and so on. But if the number is not higher than 26, we just move it down to the last row. And once we have done all this and we get the final series of numbers, we just translate those numbers back to letters. And then you have the encrypted message at the bottom, NDFKREDIHV and so on. And that is now encrypted using our one-time pad. To decipher the message you have received that has been encrypted with a one-time pad, you just do the exact same operation but in reverse. So here's the encrypted message we just encrypted, and let's say that now we are the recipient and we have received this message. So the first thing we do is, as we did before, we translate each of these letters into a number, as I've done here. And then we take our key, which we also have. We have the second copy of the key, and we translate all of those letters into numbers as well. And now, instead of adding, we start by subtracting. So we take the number we get from the encrypted message, and we subtract the number we get from the key. So this gives us some numbers that are negative, and some numbers that are not. And now again we do the modulo 26 thing, but in this case, since we have negative numbers, we add 26 for each number that is lower than 1. So before we subtracted for each number that was higher than 26, and now we add for each number that is lower than 1. And this gives us a final string of numbers. And once we translate that final string of numbers back to letters, we have the original test message deciphered. For one-time pads, as you have figured out by now, you have to make sure that the keys have been distributed beforehand. And a one-time pad is typically encoded and decoded by hand because that is simply the most secure way of doing it. Because once you've done the encoding and decoding procedure, you can simply burn all the traces. So you can burn your notepad and you can burn your key. You can also, of course, burn your clear text message, and then there's no trace left of what it actually said originally. So then it doesn't matter if someone intercepted your encrypted message, because then there is no way to decrypt it anymore. So how do you distribute a key? Well, as you can see here, you'd have a miniature kind of pad or a roll of paper or something like that with the keys printed on it, and also with some kind of numbering, so you can see which keys you have used and which keys you have remaining. Once you have used up your entire pad or roll or whatever it is kind of format you use of your keys, then you will simply be issued a new pad or roll with keys from your organization that has recruited you, or the organization you are working for. And this is how number stations can still work today. Since one-time pads are so secure, and since you can do pretty much all the decoding by hand, number stations are still viable, even though it's very easy to intercept and record their transmissions. It is basically impossible to break the encryption of these transmissions as long as they fulfill the previously mentioned conditions. And there have been examples where some of the organizations running number stations have gotten a bit sloppy and maybe not used perfectly random keys, or not random enough, I should say, or made some other mistake or reused keys, and that has opened them up for code breaking. But if they do everything right and have sufficiently random keys and never reuse them, then it is still a very secure mode of communication. A final word is that you can also use a table like this to convert between letters and numbers. Instead of just numbering the letters, you can have something that is a little bit more intricate, like this one. This one was issued by the East German Stasi for its clandestine communications users. So as you can see, this includes other kinds of signs as well, not just letters, and some specific code words and such. So there are a number of different variations on this theme, just to give you some idea of that you do not have to do it exactly the way I did it, the way I showed you. You can also have some variations on this theme using this kind of complementary encryption or translation table, I should say. Based on this, we can conclude that communicating in secret with intelligence officers and recruited agents on foreign soil is vital in order to exercise command and control. We can also see that this kind of communications present an opportunity as well as a vulnerability. Intelligence agencies can exploit the opportunity presented by these clandestine communications to intercept, localize, and break the ciphers of the enemy, but it also at the same time has to protect its own communications. Encryption. As for encryption, even though most encryption today, as you probably know, is software-based, pen and paper can still be used to achieve very good security in the form of one-time pads. And code breaking, general AI platforms or large language models are actually very bad at code breaking, as I've shown. Dedicated software works fine though, but you still need to know what kind of software to use and how to use it.
That's all I had for this time, but now, as you know, all you need a little bit of practice, and then you can actually be better at code breaking than a modern AI. Also, now you also know that all you need is to go out, get yourself an inexpensive receiver, rig up an antenna, and then you too can tune in your own numbers stations. And let's not forget, all you need is pen and paper to encrypt your own communications. So get started, teach your friends how to do it, and then you can all enjoy secure communications completely analog. Thank you for listening and watching.